Okay. Now, what we have here is the relationship between theta, omega, and alpha. Okay? What we've established is that this graph gives you this graph. We've seen how. And this graph gives you this graph. We've seen how that does. And you have all that in your table. And you've worked that out in your table. So none of this should be a surprise. From what we've just seen, we know that to get from this graph to this graph, we just take the slopes. Values of omega in this graph are the slopes of this graph. And the values of alpha here are the slopes of this graph in the way we've seen, specific way we've seen. Now at this point, I could say if alpha of t is alpha constant, some constant value, some number that doesn't change, then the question is what's omega of t? Now we can't dive into that question because one person at least is taking calculus concurrently. So we're going to wait a few weeks until we get a few rules for derivatives. And these are the first rules you're going to get, and you're going to get them pretty soon. Okay? We're going to wait for you to get those. But if you do know about the derivatives, you can understand that if alpha of t equals alpha constant, then omega of t has to equal alpha constant times t plus an integration constant, because to get this omega from this alpha, you're going to reverse the derivative. You're going to do an integration. And at the simplest level, though, I'll just assert this and say, if you take the derivative of this, you get this. Okay? And then you can verify that the derivative of this is this. And this is the most general function whose derivative equals this. So if you have a uniform alpha, and alpha is just your angular acceleration. It's the rate at which your angular velocity changes. Just like your angular velocity is the rate at which your angular position changes, okay? Each of these is a rate of change of the previous. So, I guess I could say rate of change also, because rate of change is identified with derivative, okay? If you're taking calculus and haven't gotten to the derivative, rate of change. Which you understand just fine because the table looked great, okay? So, the rate of change of this is this, the rate of change of this function is this function. Calculus gives you an easy way to do that if this is constant. If this is the case, then we can say the following. Constant alpha, we have these two equations that come directly from basically what you learned in the first month of calculus, okay? So these two equations are fundamental. For omega is omega as a function of t, theta is theta as a function of t. if you have an object accelerating uniformly, okay, here, this is equivalent analog to this. That thing's accelerating down the table. Thank you. I wasn't sure about that. Okay? It's accelerating as it goes up the table. That's a negative acceleration. Now it's accelerating back down, right? Okay? We don't describe the position of this by theta, although we could, because it's rotating. We could measure rotations here, right? Okay? And matter of fact, that might be a pretty good thing to do prior to this long exercise. Okay. And we could convert that to distance along the table, right? Okay. So, for distance along the table, going to say for motion on a straight line, v, your velocity, equals at plus v naught. We use a instead of alpha for the acceleration, but it's the rate of change of velocity. Okay? And velocity is the rate of change of position. These are dual equations. Their equations are similar, but not exactly the same thing. And they have exactly the same form. Did we see how the form of this equation is identical to the form of this equation? It's just that instead of omega, which is rotational velocity, angular velocity, we're using v, which is just how fast you're going. We use speedometer measures it on your car, right? A is your acceleration, which is the rate of change of velocity, just like alpha is the rate of change of omega. Okay? And I'm kind of rubbing your noses in this with all this analysis of this data because you really want to understand these things. Easier to understand in terms of this, okay? But then motion along a straight line is real important stuff too, right? So if you understand it here, you can understand it here. So, and it, totally analogous. It's just that we use a instead of alpha if you're moving along a straight line. Okay? We use b instead of omega for velocity, and we use x for position instead of theta. Okay? It's all the same stuff. And most of what you're going to do for homework is you're going to see this, not this. Okay? We started with this because we have all this detailed data about this motion that we don't have for any linear motion and can't get without going to a black box. Okay? And we might or might not look at the black box on Friday. Now there we are. Now there are two more equations. Okay? I'm not going to write them down because I don't remember exactly how your book forms them. But I'll write down the equations I kind of think that you'll see in your book, which is that it's either this or something very similar to it. Okay? And that's the question. Okay? And this. I'm not sure that your book uses this one. There are different ways you can arrange these. You can derive this from these two. You just eliminate t. Solve this equation for t. You get t equals v minus v naught over a. Okay? And you plug it in here. And you're going to be squaring that and stuff like that, and then this pops out. Okay? And you eliminate acceleration here. Solve this for acceleration and plug it in here, and you get this. I could do that. It's fairly simple algebra. But what you're going to see in WebAssign is problems that use a set of equations like this. So we're going to see how those equations might be used. Okay? I'm going to demonstrate a little bit of that in the last 15 minutes here.